Hi everybody. Today we're going to have a look at antidifferentiation, which as it sounds is the opposite operation to differentiation. So let's have a quick review of what it is to differentiate and then what it is to antidifferentiate. So to differentiate, we start with the function y equals ax to the power of n, and if we differentiate that, we multiply a by the power and reduce the power itself. And we've done lots of examples of these. So if we had y equals 3x squared, multiply 2 by 3 gives us 6, reduce the power by 1 is x to the 1, which is just x. Easy enough. Now to antidifferentiate, we're going to perform the same operations in reverse order. So rather than decrease the power, we're going to increase the power. Rather than multiplying, we're going to divide. So if the derivative is a n x n take 1, then the original function is going to be y equals ax to the n, and the n's will cancel. Increase n by 1 by n take 1 by 1 will get n. Divide by n, the n's will cancel out. You'll be left with axn. Easy enough. Let's do one though. So if the derivative's 6x, then the original function will be y equals the power increased by 1, divide by it, so the power was 1, it's now 2, divide by 2, 6 divided by 2 is 3x squared, and if we want to check our answer, 2 times 3 is 6, reduce the power by 1 is 6x, what we started with. Now this reverse process is called antidifferentiation, and after we look at Riemann sums, we'll look at integrals, which is a very similar operation and a lot more useful in general. So, one problem that we have is that when we differentiate a constant, we get 0, which sounds fine, but from 0, our antidifferentiation process won't give us back 25. In fact, what it'll say to us is that it can be any number at all. So if dy dx was 0, even if we put here x to the negative 1, which would get us back to x to the 1, it still wouldn't tell us what the value is. It's still not going to help us that much. So what it does mean is that it could be a whole range of values, and typically we call it c. So if we differentiated y equals 2, dy dx equals 0. If we differentiated y equals 2x plus 1, dy dx equals 2, there's no effect on the equation of it being here. If I did, that's probably not the best example, let me try again. If this was y equals 2x plus 5, that's going to give us 2. If I do 2x plus 1, that's going to give us 2. If I try and anti-differentiate 2, I'll get the 2x, but I won't get the 5. The constant is lost in the process. That's probably a better case. So we typically allocate the variable c to indicate the constant could have been used. It might be 0. So when we do our solutions, you'll see that 2x integrates to x squared, as per our process, plus some constant. We don't know what it is. Dy dx equals x squared, increase the power, becomes 3, divide becomes 3x cubed, plus some constant. And it will even work for polynomial expressions. So if we have 2x squared plus x plus 3, increase the power, divide by it, increase the power, divide by it, put the x there, and don't forget the constant. And this is a constant reminder that when you're antidifferentiating, don't forget the constant. Okay, now we can't find that value of c if we're given a bit more information. So in this case, we're given the derivative being 2x plus 3, and we know that the original function y passes through 2, 3. Now once we do that, we can use it to solve for c. So if we integrate I'm using the words already, if we anti-differentiate 2x plus 3, we'll end up with x squared plus 3x plus c. Now given that y passes through 2, 3, we can substitute in 3 for y and 2 for x and solve for c. c gives us negative 7. We can rewrite our formula now with c having a value, and then we could go on and solve some other problems with it if we had to. Now calculators can do this process for us very nicely, so let me bring it up. Now it's going to do it using integration, which is a process from next year, but it will give you the antiderivative, which is what we're going to use it for. So to do so, find your Maths 3 template. Is it Maths 3 or Maths 2? Maths 2 template. And this is what we're going to use to find our antiderivative, this button over here. And it will produce this template. We can ignore these boxes here for the moment. And all we're going to do is we're going to stick in 2x plus 3, because we know the answer to that already, and dx. And lo and behold, it gives us our x squared plus 3x, but what it doesn't do is give us our plus c, so we have to always remember to stick that on. If we'd wanted to work out what the minus 7 was, we could have done that too. We can go, what is it? It would be 3 and 2, wasn't it? 3 equals answer pipe x equals 2. Oops, what did I do? Well, let's say 3 equals answer. Let's get that out first. And then we end up with our 3 equals x squared plus 3x. And we have to put our plus c on the end of that, don't we? Plus c. Now we can substitute in x equals, what is it? 2, wasn't it? Didn't do that very well, did it? Oh, that's because this got stuffed. All right, let's do this properly. We'll end up with 3 equals x squared plus 3x plus c. Gives us that equation. Then we're going to solve for c. Oh no, we're not. We're going to substitute in for x first. Because I didn't substitute in for that x over there or this x over here. I'm not doing this very well at all, am I? 3 squared. So 3 equals 2 squared plus 3 times 2 plus c. Now we're going to solve for c. We don't really need to do this, but we'll do it anyway. Solve answer comma c. And now we're going to get our c equals minus 7 as per before, and we could write our equation out. Well, I hope my bumbling here was helpful, and I will see you in the next one. Thanks, everyone.